Welcome back to Codex. Today's speaker is Professor Kathlén Kohn from KTH. Professor Kohn is an expert in nonlinear algebra and its applications. Today she's speaking to us about algebraic neural network theory. Take it away, Kathlén.
Yes, thank you very much for the nice introduction. So as I just said, this is an interactive talk, so I'm going to ask lots of questions. But you're also welcome to ask me questions, by the way. It goes both ways here, okay? So first, let me tell you what I am not doing for the context. I don't know exactly about the knowledge scape of the audience. So, but some of you might be familiar with that one popular approach in deep learning theory is the so-called NTK approach, where NTK stands for neural tangent kernel. And this is a simplified picture of this approach. But essentially, the gist of it is that if you want to study a network, you increase the width of its layers until you get an infinitely wide network, and that essentially linearizes your model, which is now by definition an infinite dimensional model, but because of its linear properties, it's easier to study. And then you try to draw conclusions from this limit to your original network. And this is not what we're doing now, okay? I want to do essentially, in some sense, the opposite, okay? So I call this the AG approach, this stands for algebraic geometry, where I have a target network that I want to study, but I am approximating it by algebraic networks. So now my target network is in the limit, and I'm trying to draw conclusions in the limit from a family of other networks that go there. And yeah, so there's quite different types of flavors, not just because one is in the limit, the other is from the limit, but also in the NTK world, as you essentially study linear models that by definition are infinite dimensional. And here I'm studying non-linear models whose non-linearity is sort of controlled in the polynomial way, that live in finite dimensional spaces. Okay, so if that is sort of clear, so we're going to do the right-hand side thing. Okay, so just in case, since I really don't know, and if there's PhD students or undergraduate students, just in case you have never seen how its approximation could potentially work, this is just Stone-Weierstrass, which says in this case that if you have some function on a compact set and the function is continuous, then you can approximate it uniformly by polynomials. And that is the type of approximation that you want to have in mind. Okay. Okay, here every time you see a question that's highlighted in orange, that means there's a question for you guys, okay? So let me just sort of, warm up with some easy examples. So in multi-layer perceptrons, the standard way of how they are defined is here on the slide in this alternating pink and purple composition of functions. So the purple alphas are the learnable affine linear functions in each layer. And then in between, one has some pink non-linearity that you apply entry-wise. And in my algebraic geometry approach, I'm going to assume that this pink sigma activation function is a univariate polynomial. So there's a baby example in the second half of the slides, where I have a two-layer network, and the layers are very tiny, as you can see, and I just have a squared activation function in the middle. And now I want to ask someone to tell me what type of functions does this network parameterize? I hope someone is brave enough.
Quadratics?
Yes, you get quadratic functions in X and Y. That's what you meant?
Yes.
So here I spelled it out to be sure. So you get quadratic polynomials, homogeneous of degree 2 in these variables X and Y, which are the inputs of the network. And this is how it is. Like if you expand this thing, you get these coefficients capital A, B, C. capital A, B, and capital B, and capital C. Another question is, next question you could ask, okay, so every time I'm sort of thinking of such a network function, it's a quadratic polynomial, but can I get all such degree 2 polynomials? Or in other words, are all values for the green capital A, B, C possible? What do you think? This is maybe just a guess at this point, but
I would hope so, because there's 6 parameters that you have that you can play with. So it seems like getting 3 out should be possible.
Yeah. I mean, this is not always true, but yes, it is true in this example. So just, I mean, this was not, I didn't ask you to prove it. So yes, in this case, it is possible. You're going to get everything. So now what happens if I do replace my x squared with x cubed?
Homogeneous cubics.
Yes, very good. I love this. Yes, this is a homogeneous cubic polynomials. I have spelled them out again. I'm so kind. So here you have them. You have 4 coefficients, A through D. And same question, can you get all of them? I still have 6 parameters and 4 things.
I would guess no, because otherwise you would have started with this.
Right.
Yeah.
Exactly. So this is just yeah.
But also there's like you can pull a scalar out of the matrix at the price of a cube. So there's like the 6 parameters is fake. There's really probably 5 or so. And 5 to 4 seems dodgy.
I see. Yes. So I mean, you have to, yes, this is not a formal argument, but yes, the way I set up the question, you might guess it's not. And you can check this on your way home later or something. Like, here's a concrete example. This is a concrete choice of points that you cannot get. It's very easy for this one to, I mean, reasonably easy to see by hand, but we're not doing this now. I'm too tired. It's late here, and I already gave a talk today, actually. This is my second and so on. But in any case, on the right-hand side, I try to make a picture. This is not the best picture, but so what is actually true? You see, I have these 4 coefficients, capital A through D. So this whole set of functions lives in R4. And it is, in fact, a 4-dimensional set. So Dustin, you are sort of right. After some cancellation, it's more like just 5 parameters mapping to 4, and you actually do get a 4-dimensional thing. But you do not get all of the 4-dimensional ambient space. And I'm sort of, yeah, here's this beautiful surface, and everything on the red side of the surface is inside your model, and everything on the yellow side is not. Okay. Does that picture roughly make sense? What I want to say here. And you can, by the way, be way more precise. So the surface itself is not part of the model, but you see that the surface has this has a singular curve on top in my picture. That curve is in your model. So this is a very sort of interesting example, which is not Euclidean closed set of functions as a subset in R4. Okay. If there's no questions about this, now here's a more general definition. Okay, so for me, I like to call these set of functions neuromanifolds, because this is inspired by Amari, who called them like that. And you could define this on any parametric machine learning model, which is, for me, just a map that eats parameters and inputs and then produces an output. And I mean, the parameters are what we typically want to learn when we do machine learning. And then for each fixed choice of parameters, this is just such a function from input to output space. And the collection of all of these functions is the neuromanifold. And we have essentially just computed some neuromanifolds, or the last one we haven't technically computed here, but I have promised you this is how it is. And so in this example architecture, we have seen that when sigma is just x squared, you get all quadratic polynomials. And when sigma is x cubed, then at least maybe I could convince you that it's some proper subset of the cubic polynomials. And now just, okay, breathe. Okay, super easy question. What happens if you do an easier thing even? Like, what if I just do linear nets? So I just have I have no activation, or it's just the identity in this architecture. Then what you get? It's almost stupid.
Yeah, I think you should get all linear functionals, right?
Yeah, exactly. You get all linear functionals, but I'm asking this question because I have a different question. Namely, what if I change the architecture a little bit to this? Then what do you get now? So I still want just linear activation or no activation, whatever you want to think about.
Rank 1.
Right.
Yes, exactly. Also good. So now I get something slightly more interesting, namely the rank 1 2x2 matrices. Exactly. And I like those because these are algebraic varieties. So what happens? This is the easiest network architecture to just generalize, and you can do it now, no matter if you're tired and stuff. So if I have a bunch of linear functions that I just compose, then what is the neuromanifold? If I have such a deep linear network.
Is it just going to be all the at most rank smallest dimension of a layer maps from
Exactly.
RD1 to, yeah.
Exactly that. Very nicely formulated. Yeah, this is exactly what the neuromanifold is, pretty explicit. Okay, and so as I tried to tell you, I care a lot about algebraic networks. And so for the MLP setting, multilayer perceptron setting, this would mean I'm interested in deep, fully connected neural networks where the activation function is not linear, but is maybe some polynomial of degree delta or something, okay? And then I cannot just easily tell you what the neuromanifold is, like in the linear case, of course, but I can tell you that it lives in a finite dimensional vector space. Is this clear? Like, can somebody tell me what this vector space exactly is? What should be the ambient space of this?
So you got as many variables as like all these matrices things. So you do like di times di minus 1, then you add all those up. But then those are the variables, and then your degree is at most, is that a delta for the degree of sigma?
Yeah, it's supposed
So
to be.
I add delta to itself L times, maybe L minus 1 for...
Yeah, exactly, something like that. I just wanted you to think about for a second, because if you just write this formula, it looks a little bit ugly, but somehow, I mean, my input variables are just it's just D0, like what is the number of inputs that sort of the first layer has. So I have this many actual input variables, if you think about the previous examples. But I have for every output of the network, this is like its own polynomial function. Yeah? So I have sort of DL many polynomial functions in D0 variables, and each of these functions is bounded by some degree, which is delta to the L minus 1. So it's I don't know, it depends on what your preferred flavor of math is, whether you consider it as technical or not, but it is not so hard to see, and it's a nice finite dimensional vector space, okay? And why is this cool? Because I say that polynomial MLPs are the only ones with that property. Why is this? I didn't put this as a question for the audience, but can somebody in the audience tell me why this is true?
Something about compositional algebras that I don't know?
No, it's a different result that I'm 100% sure you do know. That is a machine learning result, not an algebra result.
If you have a non-polynomial activation function, you get universal approximators, and that might lead you to having an infinite dimensional like span.
Exactly. It is one way of interpreting the universal approximation theory. And you can either think of it as a corollary of it, but actually, okay, there are several papers proving it. I like this paper a lot. And this is a screenshot from that 93 paper. And the very first thing they prove is this. So they sort of use it to prove universal approximation. So I take a screenshot and it's not exactly well defined, but what you're seeing here, this is actually just a single layer MLP, where sigma is again the activation. And it is also very stupid in the sense that that single layer, it doesn't even have a matrix, it just has a vector. Okay, so this is just taking the inner product with a vector and then add some bias thing and then apply your activation, okay? And the linear span of this is dense in the space of continuous function if and only if sigma is not a polynomial. So in particular, if sigma is not a polynomial, I mean, if it wants to be dense in the continuous functions, then that linear span should be pretty infinite dimensional. And I think this is, that's why, because of the universal approximation theory, people typically don't like polynomials. Oh, because they don't work. But I think it's great, because if I want to do sort of any approach that approximates a target network whose neuromanifold by this thing is going to live in this span in infinite dimensional space, if I want to have some approximation of neuromanifolds that themselves live in finite dimensional spaces, I do not have so many choices. This says that essentially the only data-independent approach that is only based on the architecture, at least for MLPs, is to do it with this polynomial way. Okay, so it's a very natural choice to do this type of approximation. Any questions about that? Okay, good. Then, to take this just one tiny little step further, and this is like also a very easy result, not difficult to see at least. So now let me assume I am in this polynomial world, so I'm having some neuromanifold, but it could actually be any subset, some subset of the space of polynomial functions. So this is again DL many functions and D0 variables of some bounded degree. And now I would like to do some loss minimization. And on this slide, I'm doing the mean squared error loss, which is very standard. Yeah, so I mean, given some finite data set S, I would like to minimize this loss function that I define here that just wants all the f of a's to be close in Euclidean distance to the output b's. Okay, and so what I'm saying is that in this proposition, I'm saying that minimizing the mean squared error loss over such a subset of these polynomial functions is actually the same thing as minimizing some sort of pseudo distance to some fixed point that lives in the same ambient space. And I say it's very easy to see why that is. But at least, yeah, I don't know. Does somebody see why that is? Or
Yeah, it
has
feels
seen
like,
that? Yes,
like
Dustin?
I visualize least squares as being projection theorem in the codomain of the model that I'm training. So this feels like a nonlinear least squares kind of argument.
Yes, exactly. This is kind of a standard type of polynomial regression type of argument. So this is sort of, I mean, in this, this trick when you go, when you show that polynomial regression is just linear regression by considering all the monomials that appear. I like to call this the Veronese embedding. Now, this is just the same thing, but where my polynomial regression problem is sort of a constraint problem, because I have a constraint set, which is my neuromanifold. So that's sort of what is roughly going on here. So I try to write a proof. I'm not sure if we have time for it or something, but it's sort of this thing, okay? Like I just wrote it. If you say you have a single output, then it's just easier to write. And again, the standard trick to go from polynomial to linear regression is in all the input variables, you're writing down the map that computes all the monomials of whatever degree you need. And then your polynomial functions, then you can think of them just as coefficient vectors. And then you're just back in your linear algebra setting. And now if you now you have to sort of take the data into account. Yeah, so I take all the input data and push them into a matrix, and I take all the output data and I push them into a different matrix. But for the input data, I have to apply this Veronese embedding so that I can write this as a linear algebra product. And now the mean squared error loss has become this thing here, okay, where you have this matrix A times my coefficient vector C should be close to, well, B is actually a vector here, to the vector B. And how can you solve this? Well, then you can do it by taking the pseudo inverse that gets you the matrix A on the other side. But this is now something that you, if you have never seen this before, you have to convince yourself of. If you, with the pseudo inverse, take A to the other side, then the standard Euclidean distance changes to like a different Euclidean type distance that depends on the covariance of this input data. And this is, I don't know, somebody seen this? If not, you can just do it for dinner or something. It's not so hard. But I find this very nice. There's some observations. So mean square error loss is now really sort of the same thing as minimizing, like doing a closest point type of problem. And this point is this green point G that depends on the input and the output data. And the distance, the pseudo distance that I have to work with, only depends on the input data. And whenever I don't have enough data somehow, if I don't have enough data to cover my whole ambient space, then this covariance matrix is actually going to be rank deficient. And so it is literally going to be a pseudo metric and not a true norm or something like that. But on top of that, even if you want to prove results in sort of the big data regime, where you say, oh, I have so much data, I don't care, I'm just assuming it's large enough, and this is an actual distance, then this gives you potentially nice tools to prove something like this, because, I mean, people have studied distance problems like since forever. But these distances are a little bit nasty. Because this matrix A transpose A is not a generic positive definite matrix or something like that. These are sort of special. And does anybody see why this is, or what type of matrices did you have a feeling for that these typically are? And sort of there's two orange questions actually. Sort of, I mean, the pseudo distance is not really a generic type of positive definite matrix, but this green point, the green point is arbitrary. Okay, so if I sort of have generic, noisy enough data, this green point can be any point in the ambient space. So that's sort of nice, maybe, if you want to make some theory.
You definitely have rank bounds on A transpose A, so it can't be completely arbitrary positive definite.
What do I have on A? I didn't catch it just acoustically.
I mean, depending on your like dimension of V, then your A transpose A has a bound on what its potential rank can be, and so therefore it can't be all the possible symmetric, like all the possible positive definite matrices of any rank of that size.
Yes, so that is sort of what I wrote in point 2. But even if you have like so much data that you are way larger than your ambient space, then A transpose A is going to be full rank. This is okay. No, I'm also very bad at linear algebra on the fly, but believe me, it's not a full rank matrix, but it's still, so it's full rank, it's symmetric. It is positive definite, but I cannot get the whole cone of positive definite matrices. Maybe, okay.
I mean, if it's real input data, then that tends to be coming from some bounded domain.
Yes, that too. But even if I assume I could get any data, there's whatever you want, you plug in all the tuples, even if you don't make any restriction on your data. I mean, this is sort of also interesting. You could, of course, think about where does my data live on some domain, or does my data come from some distribution? And this does apply also some distribution on these matrices. But I'm like even asking an easier algebraic inspired question, like what if I just plug in all the possible data and I'm just allowed to do whatever, still not getting everything. So here I try to outline the proof where you get all vectors, but that's just basically algebra, not so interesting. The more interesting thing is what type of matrices do you get? And I try to illustrate this here. So if you are computing this product, so each row of A is like this row of monomials. And then if you multiply this, you get entries where each entry is sort of a monomial of a fixed shape. And then you sum over a bunch of input data. I'm not sure if one can see this. But the point is that a monomial of fixed shape can be factorized into smaller monomials in several ways, and that's why you get linear relations between the entries of these matrices. So here's like an easy example. If you do, imagine I have a very, very, very tiny, well, I have a stupid network with a single input. Okay, you typically don't have that, but just imagine for now it has a single input neuron. Then the vector of monomials I need to consider is just this type of standard rational normal curve type of embedding. I don't know what you would call this from a non-algebraic perspective, but you just take all the monomials in the single variable x. And so this is what is going to be the rows of my matrix A, where each row comes from a different input data point. And so this is a Vandermonde matrix. Okay. And if you now consider like some sort of covariance of that, then you get a Hankel matrix. Can you see that? So sort of all these off diagonal, all the terms on the same off diagonal are equal. And so this is the type of positive definite matrices that you get, those that are Hankel matrices. And I find this cool because there is, why do I find this cool? Because there is, in several papers I have found where people have studied, given some matrix, find the closest Hankel matrix, right? Maybe under some other assumptions like rank bounded and Hankel, or Hankel and I don't know, something. So sort of these constraint type of finding the closest matrix towards the space of Hankel matrices has been possible. But this is not what I want to do with study here, right? I want to study like a closest point problem where the distance is given by a Hankel matrix, which is weird, and I just have never really seen this. But it seems to be what you want to do if you want to do algebraic neural network theory. Okay. So if anybody has seen something like that, I would be happy if you let me know. Just to see how this sort of generalizes, here's like an example that I call it with my 4-year-old daughter. Like I wrote a matrix and she helped me call it the symmetries, okay? So here I have 2 inputs, and to make it writable, I'm just working with bounded degree at most 2. This would parameterize the standard Veronese surface in P5. And then you get this type of, well, it's not a Hankel matrix anymore, but maybe one could consider it as like the multivariate type of extension. And you have a bunch of linear relations there. Yeah. I do not know, by the way, whether you get all positive definite matrices that have this Hankel shape for sort of arbitrarily large and noisy data. Okay, any question? Otherwise, the same thing goes through just if you have more than just one input. Okay, this is not so interesting maybe. But why am I telling you all of this? Okay, so papers on deep learning theory, many of them have focused on studying the loss landscape. And this is sort of the natural thing you want to do. And I mean, we sort of do machine learning in parameter space, because the parameter space is typically like some finite dimensional Euclidean vector space, okay, and then you do your training there. And if I just told you, I mean, if you have a non-polynomial activation function, then you also want to potentially study your problem directly there, because the neuromanifold itself lives in like an infinite dimensional space, which you can of course study, but it can be a little bit nasty. But in this algebraic world, where M itself, the neuromanifold itself is in a finite dimensional space, I think it is more natural to decouple this problem, and instead of studying the loss landscape directly, to study the neuromanifold and its parameterization really on the one hand, and that is like a completely data independent thing, and then second, to study the loss landscape directly in the function space, which is now not really harder, just because M lives in a finite dimensional vector space V, and so also its loss, the graph of the loss function, is living in a finite dimensional vector space that I can look at. And also from this perspective, it's sort of apparent that, I mean, the geometry of this neuromanifold is going to drastically affect the geometry of this loss landscape. And then questions I care about is like, okay, then what type of geometry does M even have in the first place? And second, then how exactly does it affect the geometry of the loss landscape? And of course, you can add more questions like, third, okay, now what if I do this limit? What happens in the limit if I go to analytic or continuous activations and so on? Okay, finally, another audience question. So I'm interested, for the first question I care a lot about is, what is the geometry even of this neuromanifold? But then I first need to understand in what is the framework I'm working in. So let me assume that everything is polynomial, okay? So I have a parametric machine learning model, which is a function that each parameter is an input, and that function is polynomial in both the parameters and the input, say, okay? Then I already told you the neuromanifold lives in some finite dimensional vector space of polynomial functions, but what type of subset is it? Is it a manifold, for instance? I don't know what language you have here in this seminar, so.
Is a semi-algebraic function? Oh, sorry, this isn't mu. This is the image of mu. So maybe a semi-algebraic set?
Yeah, exactly. So the neuromanifold lives in a finite dimensional vector space, and in that vector space, it is a semi-algebraic set, which means that in theory, I can send it to you via email, not just in this parametrized form by mu, but there's also implicit polynomial equations and polynomial inequalities that describe it. Okay, but of course, finding those is hard, but principally possible. Okay, and so what we're doing here in this setup of algebraic neural network theory, and assuming you want to do mean squared error loss, then you would just do Euclidean distance minimization, where your Euclidean distance is some pseudo distance on a semi-algebraic set. And you want to study sort of how that behaves, okay? And then there's many special points in semi-algebraic sets that I think are interesting. If you, for instance, study generalization questions in machine learning, and these degenerate type of points on the semi-algebraic set are sort of either the singular points in the sense of algebraic geometry, or the points that live on the boundary. So here's just a sketch. I know, Dustin, you know all of this now, but I don't know about the people in the seminar. So yeah, so how I think of this geometrically is via Voronoi cells. So I guess that many people here have seen a picture like on the top here, where given some finite set of points, people study these Voronoi cells. So the Voronoi cell of any fixed point is just all the points in the ambient space that are closest to the fixed points and not to anyone else in the given set. Okay, And of course, you want to study this, for instance, when, I don't know, your points could be satellite masts and you want to see some sort of cell phone coverage or something like this. So in many engineering disciplines, these Voronoi diagrams of finite point sets are very important, but nothing prohibits you from studying Voronoi sets of continuous objects. Okay, this is what I like to do. And so I could study Voronoi cells, for instance, of neuromanifolds. But before I do that, maybe we can do a baby example. So here's a half circle. And the half circle lives in the plane. And say I'm just doing the standard Euclidean distance. And then I mark the green point and the pink point. And what is their Voronoi cells?
Do you want me to answer? I can answer.
Yeah, anyway.
I'll say at the green point, his Voronoi cell is a ray emanating from the center of the semicircle and going through the green point.
Yes, exactly. It's just a ray.
And then the pink,
yeah, the
I
pink
would say the ray, but then also everything under the ray.
Right. So I hope everybody could sort of see this. So here is a sketch of the Voronoi cells of these 2 points. And so what's sort of interesting is that the 2 boundary points of this circle, they are different very much when it comes to this Voronoi diagram, because they are the only points that have these full dimension Voronoi cells. So that means, say I would have some sort of compact domain that contains this half circle, and that half circle would be my model, my neuromanifold, and I would have some probability distribution that covers this compact domain where I pick my data points. Then the 2 boundary points are the only ones with the property that with positive probability on the data, they would be the global minimum. So there would be global minima sort of more often than any other fixed point. And well, not just more often, but with non-negligible probability. And every other fixed point is just going to be the global minimizer with probability 0. The most reasonable probability distributions. But so that's a sort of one geometric way of phrasing that that this model, this half circle, when you do Euclidean distance types of optimization, then it's implicitly biased to its 2 boundary points. So they are sort of very important for this optimization problem. And this was sort of a sketch for boundary points on semi-algebraic sets. And then the same thing can be true for singularities. So I'm not going to define formally what singularities are, but this is just the points where your semi-algebraic set locally does not look like a vector space. Okay, so it's not a manifold there somehow in that neighborhood. So can somebody else then tell me what the Voronoi cell, or like at least one of the Voronoi cells, so either at the green or at the pink point, whatever you prefer, what you find easier.
So the like at the green, it should be like a line that's like normal to it, like shooting out.
Exactly. Very good. Very good. I would send you a cookie. I don't have one, though. I mean, I don't have one, and I can also not send it. But just another somebody else about the pink point. What is this going to be looking like? Here, more wild guesses are allowed. Like, it doesn't have to be the correct answer.
So you don't see it, but John Jasper just gestured in the air as if to say things, at least locally, things to the right of the pink point.
Yes, exactly, exactly. Very good. Yes, so this is exactly how it is. And this is a fun challenge. So, I mean, if you want to, just, want something fun for your newest PhD student, ask him or her to compute the boundary curve of this Voronoi cell. It's not too hard, but it's fun. And so, yeah, so it's sort of, it's not really a cone. This is a degree 4 curve that bounds this thing. But again, it's sort of true that the singular point on this cuspidal curve is the only one with the property that we have this sort of full dimension Voronoi cell, which is why you could geometrically argue that that model and Euclidean distance minimization on this model has some implicit bias just exactly towards the singular point. Okay, and just imagine if this literally would be a neuromanifold. Then I say this example tells you a very fundamental trade-off, okay, because of two things. So on the left thing, I would a negative property, on the right, a positive one. So let me start with the negative thing, and that has been observed long time ago in the 90s, even, again, by Amari, same person who coined the term neuromanifold. So if I would, what do you do in machine learning? You typically initialize some weights and get a point on a neuromanifold. For instance, I would get the green point. Okay, then I just sort of told you that with bigger probability, the pink point is going to be the minimizer. So from the green point, machine learning or network training wants to move towards the pink point. But when you get very close to it, your learning will have to slow down, and worse, you even get numerical instability. And this is because this singularity arises because the parameterization of this model drops rank at the singularity. And so you cannot even do backpropagation, etc. So, or in other words, your network training is actually infinite condition number sort of around at that point. Okay, and so you will not be able to, theoretically, you will not be able to go there. You would have to do something like some jumping technique, like in pruning or something, to be able to do it. Or just cut off at some point. So this is negative news for efficient optimization when you have to pass through singularities or in close proximity to them. But on the other hand, these full dimensional Voronoi cell in this baby example tells you that this solution is actually quite good, because first of all, it is in some sense stable, right? Because again, if I imagine all my training data to be like this point in the ambient space, but then if that lives in the Voronoi cell and I perturb it, then the pink point is still going to be the global minimizer. This is a little bit hard to explain in this online seminar, but I hope you see what I mean. I mean, just because this Voronoi cell is full dimensional and in the Euclidean space. So it has this nice stability property. And I think, okay, this is Kathlén's conjecture, I think that singularities of neuromanifolds always correspond to sparse networks. So they are sparse solutions, and we know this for polynomial multilayer perceptrons and for polynomial convolutional neural networks.
Sorry, when you say sparse networks, do you mean most of the weights are zero, or do you mean something else?
Yeah, doesn't necessarily have to be most, but some weights are zero. And so it depends exactly a little bit on your network architecture, what that means. So if you really think of a multilayer perceptron, the result we have proven is in fact that one of the neurons, at least one neuron, is inactive. So either all the weights that go into it are sort of zero, or that go out. So sort of in your matrices, either a column is zero or a whole row is zero. Something like that.
So Kathlén, you mentioned that these are also points that drop rank. So is that coming from what you said, that you get a row of zeros or a column of zeros? Or is there something else?
What do you mean with dropping ranks? When I talked about something being zero, so you have like a deep network. So in each layer, you have a full matrix of learnable parameters. And say now in one of the layers, there is a full zero row in that parameter matrix. But it doesn't, I mean, but the total thing is not a linear map anymore. It's not so easy to make sense of it in terms of a rank. You can do this via sort of tensor decomposition for like monomial activation functions, but if you have a very large degree generic polynomial, or even like an analytic function, then it doesn't really make sense to think about it in terms of rank, I think, as a function, right?
Talking about being slow and numerically unstable, that at these singular points, there's some sort of rank dropping either by weight matrices, or maybe you're speaking specifically to the linear neural nets. But yeah, I'm not sure.
Yes, so this rank dropping is literally about the Jacobian of your network parameterization map, right? The map that eats all the weight matrices and then computes the function. Now that has, for every fixed choice of weight matrices, that Jacobian is a matrix and that has a well-defined rank. And that is generically everywhere the same for algebraic networks, but then it drops at some places, and those can be singularities. And those are these type of singularities that I think both have the bad or worse training efficiency, but on the other hand, better generalization because of these higher, larger dimensional Voronoi cells that in dynamical systems should sort of correspond to larger attractive basins, or what you call it. Yes. More questions about this trade-off? So one thing is that whether this trade-off, because I just give you upstairs a toy example. I mean, this Caspel curve is not the neuromanifold of an actual neural network, right? And whether the singularities cause this type of trade-off between efficiency and generalization, that does depend on the type of singularity. And we have done sort of more fine-grained studies, and at this moment understand pretty well MLPs on the one hand and CNNs on the other. So this is a sketch, but the singularities that are on polynomial and multilayer perceptrons are indeed of this Caspel nature, and have exactly this thing that if you go close to them, the Jacobian drops rank, you get worse training. I mean, you get the infinite condition of your training, but on the other hand, you have these stable because of larger Voronoi cell type of arguments. But on the other hand, interestingly, polynomial convolutional neural networks do not have that behavior like at all. Okay, so these also have singularities, but the singularities are very different type. They are arising only as self-intersections. And these do not have any Jacobian rank drop anywhere. So there is no sort of infinite condition in your training like ever. And but on the other hand, these are also not really generalizing better. I mean, because the Voronoi cell here is actually, in this particular picture, it would be, I think, well, empty or just the singular point itself. So yeah, it really depends on the type of singularity that arises on your neuromanifolds, what is happening here.
It seems
yeah.
Generalization you get from CNN is by forcing the convolutional structure. Like you're forcing the solution to have convolutional structure, and then that would facilitate generalization. Whereas in the MLP case, the landscape is encouraging singular points as being your optimizers. And then those are the special points that encourage generalization.
Yeah, exactly. Maybe, yeah. Yeah, so there's many questions. I mean, in these two examples, I know exactly sort of what these singularities are, and I know that they are corresponding to sparse subnetworks. Now, subnetwork for convolutional means something slightly different, but essentially you can think of filters being smaller so that you can embed the smaller architecture into a bigger one. This is always the idea of subnetworks. And I'm sort of, for instance, one of the things that I'm interested in is that, I mean, convolutional networks are like example of when you impose translation equivariance onto an MLP. But now I could impose other group equivariances on an MLP and then study what happens to the neuromanifold. And there's many other examples where people try with other groups, actions that appear because of their chemistry application or whatnot, where somehow training does not become easier. But in the CNN case, it does. So sort of also experimentally, it's nice that training deep CNNs is sort of has better efficiency than if an MLP, and for an MLP you would have to add skip connections and so on and yada yada. But this is not true if you have some other group equivariant architecture. And so one of the things I care about is like trying to understand in geometry of neuromanifolds if I sort of mod out other group actions and to what extent I can understand that. Okay, and then maybe just one last thing. And I just added this one last thing because I saw that a few weeks ago you had a talk by Jose Rodriguez. And I just wanted to make a context between that talk and this talk. Okay, so I think, and correct me if I'm wrong, so I think that Jose Rodriguez has talked about what is the dimension of the neuromanifold, and which is equivalent to asking what is the dimension of the generic fiber of the network parametrization map. In algebraic geometry language, more machine learning languages, can you tell me if you pick a generic function in a neuromanifold, which parameters give that function? And if you cannot tell me precisely which ones, but can you at least measure how many they are in some sense by either counting them, or if it's infinitely many, then tell me what is the dimension of them, right? This is, I think, what Jose talked about. And they have a nice paper in the situation where you are studying MLPs and you have sufficiently large degree monomial activation functions. And then I think, if you remember, he did tell you that for a generic function, the only symmetries in the parameters, I mean, if I give you a parameter that gives you a function, how can I cook up new parameters that give the same function? Well, you could permute the neurons in each layer. But you can actually scale each neuron, and then you have to just sort of delete that scaling in the next layer, something like that. Does that roughly ring a bell for some of you? Or did he tell you something completely different? I don't know. Okay, people are quiet, which means that maybe he did tell you. But do you understand the result that I roughly want to say?
Yes.
Exactly. Okay, good. Yes, and so it is sort of, all these things are very intimately related. The studying of the dimension of the neuromanifold and the study of this identifiability question and the study of what is the singularities, and all of this is very, very much linked to each other. And so it's sort of along the way to get these singularity things, we have asked us the same questions for all the other three fields in this table. Okay, so for instance, if you do monomial convolutional networks, then the only thing you can do is you can have a scaling per layer. That's it. And if you would sort of mod out that scaling, then your network function becomes actually bijective almost everywhere. And regular, so it's smooth. And this is what I sort of said before in my picture. The Jacobian of your network parametrization map like never drops rank. So you can always do, back propagation. It's not a problem. It never, nothing is ever breaking. Is sort of what this says in less algebraic language. And it's almost, if you mod out the layer-wise scaling, it's almost bijective everywhere. And it's exactly not bijective at these subnetworks that cause singularities. This is how the singularities appear on the neuromanifold. And this is why these results from Jose Rodriguez style are sort of very much related to the study of these singular, or somehow a prerequisite. Okay. And yes, and then we have now this year done this generalization of these monomial results for generic large degree polynomials, which is what you want to study when you want to go the route of approximating arbitrary networks with algebraic ones via Stein-Weierstrass. Then you have to understand generic polynomials. And yeah, you can sort of read this. I mean, in an MLP case, the only thing you can do is commute neurons, and otherwise, yeah, which is surprisingly hard to prove. Of everything I told you today, this is the hardest thing to prove, although it's a super obvious result, but it is damn hard. Okay. But on the CNNs, it is much easier and they're much easier to understand. And the moment you go from monomial to polynomial, there is no symmetry anymore in the parameters. This map, as it is now projective almost everywhere. So it sort of has removed all the singularities by imposing the convolutional structure. And so I want to end with this very beautiful and very technical slide. Thank you very much.
Awesome. Well, let's thank the speaker by clicking buttons.
Nice.
I'll stop the recording here.